So this for H2DN, you prove that the kernel, reproducing kernel, is just the product of 1 upon this. And
Yes.
when we had H2D, the kernel was simply one of these factors, 1 upon
Yes.
1 minus
Yes.
omega z.
Yes. Yes.
And for the
Dimensional.
DN, yeah, dimensional. And for DN, it's turning out to be product.
Yes.
So, yeah, I'm not sure what to ask, but basically, is it some kind of general phenomena which is occurring for DN here?
Yes, we will see. Indeed, there are even abstract theorems a little bit in future. We will see that in some cases, the kernel is the product of the kernel of spaces. We will see. This is, in a sense, a special case of a more general theorem.
Okay, and that we'll see later.
Yes, yes. This is a very specific example just for H2, but we will see that in some, under some conditions, what would be the kernel of H1, H2 times Hn. We need to develop some tools to arrive at this theorem later on, and also give a meaning to this product.
Okay.
Yeah. We will see. Yeah, that's one of our goals in future. No, so there is something in the chat. Let me see. Okay, so it's the information about the Sheldon paper. I strongly recommend you to read this, and then if you are more interested, go into, more specialized book, but the paper is a perfect reference for this subject. Up to now, for almost 3, even 4 weeks, we talk about special cases, and just to show how diverse RKHS can be. And now we go more into the direction of abstract RKHS. We develop some tools, and so each of these tools are equally applicable to all the examples we have seen up to now, and to the examples that we will see in future. So, fundamental results. Well, results. The first one is about Hilbert space structure of RKHS. So more on Hilbert space. Structure of an RKHS. A very simple proposition, but extremely useful. In many occasions, we use this innocent, simple-looking theorem. So assume that H is an RKHS on a set omega. Then the linear span of kernel functions of ky y in H is dense. That's the first version of a proposition of this time. In some spaces, we can replace h here by something smaller, we do not need to consider all point of the, I wrote h, all point of omega. We do not need to consider all point of omega to obtain something which is dense. A smaller set is enough, but that's the first version of the theorem. And the proof is extremely easy. It's a standard Hilbert space technique. How to show that something is dense? Show that if F is orthogonal to this set, then F is 0. If we show this, the whole thing is equivalent to show that the set is dense. That's a technique from Hilbert space. And now, what does it mean that F is orthogonal to Ky? F orthogonal to Ky, this means that F inner product of Ky equal to 0. But from the structure that we developed, we know that this means that F at point y is equal to 0. So for any y in the set, F at point y is equal to 0. So F is identically 0. Yeah, as I said, the proof is extremely easy. It's just based on the definition that we had before. But it's amazing that it's a very strong tool in studying RKHS. Here is the first consequence of that. I mean, it has the same flavor as before. Again, Paulsen called it lemma. I mean, we can call it proposition if you like to lemma. As before, H is always an RKHS on omega. And Fn is a sequence in H. Our hypothesis is that assume that Fn goes to F under the normal H. Then for every x in this set S, F at point x is equal to the lim and goes to infinity Fn of x. In other words, convergence in H implies point-wise convergence. And a bit more than that indeed can be said. Let's see the proof of this. Proof is again based on the identity we saw before. F at point x is given by the inner product of F and the kernel in H. Therefore, absolute value of F at point x is majorized by the norm of F times the norm of Kx. X is fixed. So we can say that the absolute value of F of x is controlled by a constant which depends on x, this constant, times the norm of F. And so if we replace Fn, F by Fn, replace F minus Fn. Fn of x minus f of x in H. And so if norm of Fn minus F in H goes to 0, this implies that Fn of X goes to F of X. Again, end of the proof. Two comments about this proof. It's a proof. There is nothing wrong in it, but I believe such a detail is not needed, because let's go back to the statement of lemma.
So we know that evaluation maps are continuous, right?
I'm sorry?
We know the evaluation maps are continuous. Right?
Precisely, that's my first comment. No proof the way I wrote is needed, because it's hidden in the definition of RKHS that evaluations are continuous. So if Fn goes to F, then Fn of X should go to F. That's a part of the definition of RKHS. That's the first comment. But there is another, probably that's why such a proof is given. Uniform convergence is not part of the definition. Here, C of X that we had in the proof is the norm of Kx in H. Usually this is the case if we have a domain omega like this and X goes toward the boundary, usually Cx goes to infinity. In other words, we do not have a uniform bound for all reproducing kernel. But if, at least in the analytic setting, if we stay away from the frontier, so if omega prime is inside omega and supremum of Kx, X in omega prime is a constant which of course depends on omega prime, which is not plus infinity. So Kx is uniformly bounded on this subset. Then we can say this part, and this is not, for this we need a proof, it's not part of the definition. If Fn goes to F in norm, then Fn of X converges to F of X uniformly for X in omega prime. Or sometimes in the old notation, in some old books, Fn, this is the notation for uniform convergence. Fn uniformly goes on F on omega prime. True? This is not part of the definition. So this proof can be useful for what I mentioned here, because again, you have the same estimation. But if you are in omega prime, you can replace Cx here by a constant m, and still the same thing works. And we use this usually in oversetting analytic function spaces. So application. In all of these spaces, at least 3 of them we saw by now. We saw Hardy space, Dirichlet space, and Bergman space. I mean, and to our collection, you can add model spaces K theta, which are inside H2, and also weighted Dirichlet spaces. It will come a little bit later, and Dobranj-Rovniak spaces, which is again, they are in H2, but they are not closed. I mean, these spaces come a bit later, and the list still can continue. I mean, I'm just focused on the main 3 parts. This is open unit disk. if you stay away from frontier, a disk R, but R is strictly less than 1 on this disk. If Fn goes to F in any of these spaces I mentioned above, then Fn uniformly goes to F on a fixed dr. When we repeatedly use this property in our applications of RKHS to analytic function spaces. Okay, that's the second property. And the third one, which in conjunction with the Moore theorem, probably I will not arrive at Moore theorem this week, but it will be, that's a good point to mention about Canadian Thanksgiving. I will mention it. Not next week, the week after. Next week we do not have a course, I will explain. But the next time that we come, a Moore theorem will be one of our main theorems that I want to prove. Conjunction with this proposition shows that kernels are in one-to-one a bijection between RKHS and the function. So whenever you have a space, you have a kernel, and whenever you have a kernel, you have a space. That's the point I want to elaborate. So the easy one is this one, proposition. Let H1 and H2 be reproducing kernel Hilbert spaces on a set omega with kernels K1 and K2 respectively. Assume that the kernels coincide. K1 xy equal to K2 xy for every x and y in the domain omega. Then first things, the space, both space, I mean, the spaces coincide. I mean, H1 is equal to H2 as sets, but more than that. And for every F, now it's the same set. The norms are equal. Normal F in H1 is equal to the normal F in H2. Of course, the other way around is trivial. If, I mean, H1 is equal to H2 and you have an isometry, then kernels are equal. But the message here is that if the kernels coincide, you have the same thing.
So will it be just the norm equality or the inner product will also match?
Well, when you have norm equality here or in any other setting, you can use the polarization identity.
Yeah, okay, right.
And then this immediately implies that F and G in H1 is equal to F and G in H2.
So H1 equal to H2 as Hilbert space itself.
Yes, precisely. If the kernels, you can summarize the theorem as this. If the kernels coincide, then they coincide as Hilbert spaces. Yes, absolutely. Well, since K1 is equal to K2, I call both K. The reason is that when I want to, for example, consider K1 of X, which is K at point X and Y, it's easier to write it as this way than write it as, well, it's K1 of X by 2. If I want to write it as this way, it would be K1 then YX. It's a bit difficult to write it this way. So that is why I introduce K. And whenever I write it as a kernel function, it can be interpreted either as a kernel in a space H1 or as a kernel in a space H2. Indeed, writing this way, immediately I can define at the first glance two sets, but when you look carefully, it's just one set. W1 is the span of Kx in H1. And W2 is the linear span Kx in H2. It's just a finite linear span for the time being. But because of this, actually W1 is equal to W2. I mean, it's just one space. What do I want to do? What I want to do is to, geometrically speaking, for the time being, I don't know if H1 is equal to H2. It's my goal. So let's assume that we have this picture. I introduce W here, which is the same as W1 equal to W2 equal to W. W is in both H1 and H2. What I do is to show two things. If F,
sir,
yeah,
W closure in both, W closure in H1 is H1 and in H2 it is H2.
yes, because of this identity here.
I think the first lemma or forum we did, right?
Yeah, no, just because of this. When I write K index Y or K index X, well, it can be interpreted as K1 index X or K2 index X. It's the same thing. But if I write it this way, it stays in H1. If I write using K2, it will be in H2. So it's the same function space, but K equal to K1 equal to K2 says that it's in H1 and also in H2. True? And also, I want to show that for every F in this W, we have an isometry. The norm are equal. Why do we have this? Another way to realize that it really doesn't matter that we consider it as in H1 or in H2 is this interpretation. Consider F is in W. A span, what does mean? It means that F is a finite combination of alpha j, k, x, j. That's the definition of a span, j from 1 to n. True, because it's in a span of kx, x in omega. Up to now, there is no indication that f should be in h1 or h2. But when you evaluate f at point x, it becomes alpha j, k, x, j at point x. Based on the definition of k, it's j from 1 to n alpha j, k, capital K now, capital K, x and xj. Now go back to what we had before, to this. First, I can write f of x equal to sum j from 1 to n alpha j. Instead of k, I write k1, because k is equal to k1. And so I can write alpha j, little k1, index xj at point x. And this is a function in h1, which is evaluated at the point x. So this interpretation shows that f is in h1. Precisely the same thing can be repeated up to here, except that the first line is the same, except that instead of k1, now I put k2 because k is also equal to k2. And so it's sum alpha j, little k2, index xj at point x. And now this is a function in h2, evaluated at point x, which implies that f is also in h2. That's a more detailed version of what I said. So I have was that? So I have something like this. I have a W, a set of functions which live inside H1 and live inside H2. That W is dense in H1 and dense in H2 is a consequence of previous lemma. But now I can say a bit more. I want to say that norm of f in H1 is equal to norm of f in H2. It's an isometry. If the identity map is an isometry. And again, this is not something difficult to prove. It's similar to what I did here. Really similar to what I did here to show that f is in H1 and H2. How do we do that? If f is equal to the sum of alpha j, k, x, j, what is the norm of f in H1 squared? Note that I can write this as sum alpha j, k1, xj, because they are the same. And the summation is j from 1 to n, j from 1 to n. That would be sum over j alpha j, k1, xj and sum over I. Usually you put I here, the other one j, alpha j xj. And when we develop the summation, the inner product, we can take this out and take this out because it's a finite sum. Sum over I, sum over j, alpha I, alpha j, k1 at point xj, index xj, and k1 index x. Everything is in h1. And now so alpha j. We know what is this. It's the value of this kernel at point xj. So it's k1 xj xi. The value of this at the point xj is precisely equal to this. And do the same with h1 replaced by h2. Similarly, if I do the same calculation, normal f in h2 squared, doing the same thing, I arrive at the same summation, but at the end I will have k2 xj xi. Again, even though I have used this before, by using the fact that k1 equal to k2 equal to k, immediately I conclude that the normal f in h1 is equal to the normal f in h2. So I have a dense subset in h1, which is with respect to the normal h1, which is dense also in h2 with respect to the normal h2, and also it's an isometry. So what can I say for the whole, for an arbitrary element? So the last step, take let f be an arbitrary element of h1. W equal to W1 is dense in H1. Therefore, there is a sequence Fn in W such that Fn converges to F in the space H1. The convergence is in H1. That's one thing. Consequence of this convergence. Two things. First, Fn of x goes to f of x for every x is in omega. If we have convergence in norm, we have convergence at each point. Second, the fact that Fn converges to f in H1, this implies that Fn is Cauchy in H1. But in fact, Fn is in W. And norm of Fn in H1 is equal to the norm of Fn in H2. Even we can replace Fn by Fn minus Fm because W is a linear manifold. So this implies that Fn is Cauchy in H2. H2 is complete. So there is a G in H2 such that Fn converges to G in H2. Again, using the fact that convergence in norm implies pointwise convergence, this implies that Fn of x goes to G of x for every x in omega. And now compare this with this one. Fn goes to F and Fn goes to G. Comparison tells us that thus f of x is equal to g of x for every x, which is the same thing as saying that f is equal to g, so f is in H2. I started with an element in H1, a bit above, yeah. I started with an element of H1. Conclusion was that this element is in H2. In other words, H1 is a subset of H2. Now change the role of H1 and H2. Similarly, H2 is a subset of H1. Therefore, as in short, H1 is the same set as H2. And indeed, more than that, it's kind of hidden in the proof of H1 subset of H2. What happened? No, let's see. It's hidden in the proof of H1 is a subset of H2. The same sequence which goes to F in H1, the same sequence goes to F in H2. Remember, G is equal to H. I just proved that. So, but you can also start from beginning, not referencing to this, saying that for every F in H1, which is equal to H2, there is a sequence Fn in W such that Fn goes to F in H1 and Fn goes to F in H2. We saw it this above. And use the fact that norm of Fn as an element of H1 is the same as norm of Fn as an element of H2 for any n. Now you let n go to infinity. You obtain normal f as an element of H1 is equal to the normal f as an element of H2. That finishes the proof. And as I mentioned, based on the question which was asked, norm of f in H1 equal to normal f in H2. Indeed, that's equivalent to say that for every f and g, the inner product f and g is equal to the inner product of f and g in H2. That's one direction is trivial. The other direction, this one, is a consequence of polarizing identity or polarization identity. This is a typical example that we see in RKHS. Many times in this proof and many proofs that coming in future, you will see that we use the fact that convergence in the norm implies pointwise convergence or uniform convergence on a set which is away from the frontier, and we deduce conclusions after this. So please look at this proof again and again, because it will come in some other lemmas and proposition in future too. Well, so up to now,
Sir, may I ask you question?
yes.
So, what we have proved that if we take two subspace of functions on a same set omega, which are RKHs,
Yes.
and their kernel match, then they will be same as
Yes.
set and Hilbert space and everything as RKHs.
Yes.
And we had seen that every RKHs had given us a kernel.
That's our next is a Moore theorem. We need to develop some tool to arrive at that theorem. Up to now, this is my comment. I say that if we have H1 and H2 and K1 is equal to K2, we conclude that H1 is equal to H2. So the function spaces are given. If the kernels coincide, the space coincide too. That's half of indeed the easy half. The other, not the function space is given, a K is given. A kernel is given with some properties. Is there a space H such that for this space, the kernel is K? That's an important question.
Okay. Okay, my question was a little bit different actually. Yeah.
I'm sorry?
Yeah, please go ahead. My question was a little bit different. I'll ask it later.
Sure. So this is the kind of half of the story, but the easy part, the easy half. The other, which is a bit more detailed, is that the kernel is given, and we want to see if a function space exists such that for this RKHS, the kernel is precisely the one given before. And we will see the answer is yes, based on Moore theorem. And that is why, after having this result and this result, we see that between H, the space of functions, and K, the space of kernel, there is a bijection. Whenever we have H, well, K is somehow in the definition. And whenever we have a K, we can construct an RKHS for which the kernel is already given. So if I misunderstood your question, please go ahead and say what you wanted to ask.
Yeah, so, okay, this one is okay. So what I was trying to ask, so given a RKHS, we found a kernel.
Yeah.
And now you prove that if we have two RKHS with the same kernel, then they have to be exactly same.
Yes.
So kernel function is basically capturing everything about RKHS.
Yes.
And basically this correspondence which you told is also the same thing.
Yes.
But we have seen that given a RKHS, finding its kernel, like for the Sobolev spaces at least, the kernel which we found doesn't seem to have a direct connection. Just as a function, it doesn't seem to be directly related with how the what is RKHS basically. We calculated those, but guessing them is not something we can do. As your fourth example of Sobolev space was also like that.
I fully understand what you mean, and indeed not based on the Sobolev spaces that we saw, based on HB spaces, which I mean, one of my favorite topics. Yes, you're right. From abstract point of view, the kernel has everything in it. But it doesn't mean that when you look at the kernel, you see everything immediately. These are two different things. The information are there in the sense that it uniquely determines our space. True. But it doesn't show all the properties immediately. You have to extract them. You mentioned Sobolev spaces. It's a very good example. If you look at the kernel, for example, in the first space that we consider, the kernel was like this. Kx at 1 t, here 0, 1, tx. It was a linear map, linear line here and another line there, and with different slopes. So yeah, I agree with you. When you look at this kernel, you cannot immediately say that this kx is related to a space of absolutely continuous function such that the derivative is in L2. No, absolutely not. And you have to cook, but at the same time, the abstract theory tells us that it gives us a unique space, which is what we studied before. To get those properties, you have to work and extract the information are here, but you do not see it. No, nobody sees it in the first glance. We need to work on it and extract this information. And
yeah, so let me ask one more question. I think my question is a little bit vague.
Please allow me to, because this is related to this question you asked, to finish with HB. I will explain this after proving more theorem. If B is in H infinity and the norm of B is less than or equal to 1. In other words, an element in the unit ball of H infinity. Then consider KZW by this formula. 1 minus BW bar BZ 1 minus W bar Z. True? Well, it's a function, and based on, I will explain before Moore's theorem, it's a kernel function. So it satisfies the properties that we want from the kernel. So whatever it means, it's a kernel function or function kernel. And so based on the theorem I will prove later, it gives a unique space H such that its kernel is precisely equal to this one. So, but at this point, you cannot tell what is this space. It's a very rich theory now that it's HB, not HP, the branch Wozniak spaces, which is the topic of this week indeed. Tomorrow, is it tomorrow? Let me.
Yes, it is tomorrow.
It is tomorrow, and Dan Timothy is going to talk about it. Dan Timothy is going to talk about it. So it's a way to arrive at HB spaces, as the Branch-Wozniak spaces. Probably the fastest way you can do that, but you cannot see the properties of HB spaces after this kernel, at least not all of them immediately. You need to cook and develop a whole theory to do so. So that answers your first question. What is your second question?
Yeah, so yeah, I think you gave the answer to my first question properly. So
Okay.
my second question is like, We have similar correspondence in linear algebra, right? Let us just take a linear transformation on a vector space and they will correspond to matrices.
Yes.
Okay, there we can say something, but matrices we can't say directly what will be the linear transformation if we don't fix a basis.
Yes.
But what we do, like we have matrix operations and we have the linear on the operations on the linear operators, and they also correspond one correspondence. Like composition will correspond to the multiplication of matrices, addition will correspond to additions. Is there some kind of thing we can do here also? And let me take example of H2DN. So H2D kernel was 1 upon 1 minus omega bar z, and
Yeah.
H2DN was just the product of that.
Yes.
So let me rephrase it now like this. We had a kernel 1 upon 1 minus omega 1 bar z1 zi bar, and
Yeah.
I took n such kernels, and they correspond, and I took the product of that kernels, and
Yeah.
although you have not defined what is kernel function, but I believe that product will be a kernel function because, yeah,
Well,
we a priori know that that correspond to a particular RKHS,
in,
and that turns out to
in,
be
in,
H2DN.
yes, yes, yes. Very
So
good question. A version of this question was asked even today for when I talked about H2 of DN.
yeah,
That
right.
we saw that
I'm asking on the same
yeah,
language.
this question is related to that question and related to the subject that we will discuss in our course in future. The title is Operation on Kernels. In other words, when we add them, when we multiply them together, what happens? Do we obtain a new space? And if yes, what is that space? It's a part of our course. So yes, the answer to your question, we have operations on the kernels, some operations, I emphasize, because you mentioned linear transformation. We can add them, we can multiply by positive constant, but we cannot always, we cannot subtract them. Sometimes we can, not always. No subtraction, no multiplication by negative scalars, but we can multiply two kernels together and obtain another kernel. So we will see. And also we have Hadamard multiplication. So all these topics is in our agenda for future. On the, as I said, the title, operations on kernels. But before that, still half of the correspondence is not done. I have to prove Moore's theorem to say that whenever a kernel is given, there is a corresponding function space. When I do that, then I explore the domain, the families of kernels, and to see, given, say, a sequence or a finite number of kernels, how can I create a new kernel? And when I created a new kernel, I immediately have created a new space. This is similar to what we do in function analysis or in linear algebra. We have one vector space. We have a collection of vector spaces, and we do operation to create new vector spaces. For example, we do Cartesian product. So out of some spaces, we create a new space. Or in group theory, we have some families of groups, and out of them, either by taking the quotient or by Cartesian product or by other operation, we create a new group. Here is the same story. We have some kernels, and by some operations, we will see which operations are legitimate. By some operations, we create new kernels. And new kernels give us new function spaces. thanks to theorem, this is not proved yet. We will do it probably next week. Is that good?
Yes, sir. Thank you.
Yeah, you're welcome. Okay, 4. So again, another break. Refresh my coffee and then we come back.